So, first of all, it's very cool to be here. I especially want to thank Gian here, who invited me to this very cool event. For those of you who don't know me, my name is Raoul Scho nhof. I'm a freelancing system architect and researcher at the Fraunhofer Institute for Production and Automatization. And Gian and I are currently working on a very cool project. We tried to build an AI strategy paper for small and mid-sized companies to get in touch with AI and to learn a bit about them. We're doing that in the cooperation with the Wirtschaftsrat. And now I want to give you a little introduction about what AI really is. So we heard a little bit about AI, and I think it's not very clear how these mechanics behind the systems work. And when I tried to prepare for my presentation, I thought, hey, maybe I can look up some very cool images which show what AI is. And I was a little bit disappointed because, don't get me wrong, all of these images are very cool and fantastic, but it has nothing to do with AI. And I think if we talk about AI, we have to make ourselves clear. AI is not very fancy, but it's beautiful. And if we talk about real AI, the first thing we should ask ourselves is, what is an intelligent machine? Maybe an intelligent machine is something which can process knowledge in some way. Maybe an intelligent machine is able to outperform a human in a maybe cognitive task. Maybe intelligence isn't necessary at all. Maybe it's completely satisfying if the machine seems to be intelligent, but it isn't from the user's perspective. I want to show you a machine which I think is quite cool. For me, especially AI is basically a very simple thing. It's the art of solving a very complex problem with very simple rules. And this thing here it's not per se an AI, but it's very cool because it's a so-called Breitenberg vehicle. A Breitenberg vehicle is quite intelligent too, but it's very simple. The Breitenberg vehicle consists of only 2 light sensors and 2 motors. Whenever this Breitenberg vehicle sees a light source, light sensor 1, for example, will receive a slightly stronger signal and will drive the right motor faster. A Breitenberg vehicle is a machine which is able to find, track, and if necessary, trace any light source in a room without a computer, without even electronics, just by this simple rules. And I think this describes AI quite well. And if we talk about a real AI system, we can usually distinguish between 4 big categories of domains, of problems. We've got clustering, we've got classification, prediction, and optimization. I think clustering belongs to the not so interesting subjects. Basically what we try to do there is we try to find out if there are any groups in our data. This comes very handy if we use Amazon, for example. Whenever you buy something at Amazon, you become one data point in these big clouds, and you become assigned to one or more of these clusters, described by your age, by your gender, or by your interests in buying stuff. Amazon will try to assign you to one or more clusters. It will look up which products are associated to these clusters, and it will recommend it to you. So this is basically clustering. We've got classification, which is, from my perspective, far more interesting. Classification is basically the art of looking for patterns within data in order to assign them to a certain concept. In this case, we try to find out which picture shows what object. This is maybe a very research-driven approach, but we can use the same technology in order to assist within healthcare, to distinguish between healthy tissue and cancer tissue. We can use it to describe and analyze faces. We can read their gender from these faces. We can read their age and even the mood by just looking at the patterns within the face. So I think classification is very interesting. We are using prediction very often in the domain of stock markets to predict the next stock prices in the intraday trading within the next seconds or even minutes. We're using prediction to predict the forces on a complex mechanical system within seconds. So basically the eye behind that idea controls the artificial muscles in the simulation. This thing here belongs to the optimization domain. This strangely piece of wire is one of the most capable antennas mankind has ever built. It is an invention, but it has no inventor. It was calculated by a so-called evolutionary algorithm. And this antenna was developed for a NASA mission, and it is as capable as an antenna a human could build. At the same time, it is far lighter, far more reliable, and extremely cheap. So you see, the number of use cases we can assign to these 4 big domains are vast. But I want you to keep one important thing in mind. There's not a single AI out there who can solve all of these problems at once. When we talk about AI, we do not talk about a method. We talk about a whole bunch of different methods. Professor Ertl, which I quite admire, depicted it as a kind of pharmacy. For every issue you've got there, there's one or more solutions which can help you with your problem. Within this pharmacy, we do not have one solution. We've got, of course, neural networks. We've got other systems. We've got expert systems, we've got ontologies, we've got semantic web applications, we've got fuzzy logics, we've got search trees, and so on and so forth. So please keep in mind, AI is not a method. AI is a whole bunch of methods. And for the short period we've got here, I want to show you one very famous method, the so-called neural nets. We won't calculate them. This is not a math lecture or something like that. I want to give you the idea behind the neural network. And I think the easiest way to depict a neural network is something like this. I took this picture here at my home. I think everyone of you knows such a thing. It's a thermostat. Thermostats are quite cool because they're very simple. And I want you to imagine the following situation. Imagine you're a child, and for the first time in your life, you see the thermostat. Of course, you're curious and you try to play with this thermostat. You may turn it a little bit to the right, and you soon recognize that your temperature rises in the room. You turn it a little bit further, and you notice it's getting quite uncomfortable. Maybe you want to reverse this process, and you end up in a situation like this. I think everyone of you sees that with enough try and error, you will find the perfect position to get the perfect temperature for yourself. Please remember, our child has no idea how a central heating works. Doesn't know anything about thermodynamics. The only thing it knows is, if I turn this in the right position, it works. That's it. And basically this is the same a neural network does. The only difference in here is, instead of one signal we can manipulate, we've got tons of them. In reality we've got about several hundred, maybe a million of them. Instead of one thermostat, we've got millions and tens of millions of them. And if we try to build an application with this, let's say we want to distinguish between a real car and a toy car, we do nothing but we send in some signals. In this case, every pixel in this image, every single one becomes one signal in our neural net. This means we do not have 1 million, but 2 million signals, even in the first layer here. We calculate them, and we get a result. On the first try, all of these thermostats are completely random. We do not get any good signal out of it. But what we do now is, like a child, we try to play with these thermostats. We increase some of them, we decrease some of them. Sometimes it's getting better, sometimes it's getting worse. And after about 100,000 iterations, we end up with a nice configuration for our thermostats. And suddenly it works. The neural net has no idea how it works, but it knows, well, by trying, this seems to go well. We can do the same with a toy car, and also this configuration works for our use case. When we build an intelligent system, we have to get used to the fact that, for example, a self-driving car is not controlled by a single AI. We've got a whole bunch of them. In a self-driving car, we've got one AI for detecting objects, one AI for detecting humans, one AI for the trajectory, another AI for the navigation, and another AI maybe estimates the distances to other objects. So it's not a single AI in one system. Please keep that in mind. And for the end of this presentation, I want you to show one of my own projects. I did this project in cooperation with Airbus, and we had a quite serious use case in mind. And we wanted to prevent crowd disasters. I think a lot of you remember the Love Parade event back in 2010, where dozens of people were still alive in there. To my own surprise, crowd disasters occur quite frequently. We have a major disaster every year in the world, and smaller disasters every 3 months, approximately, every 3 weeks, sorry. So we thought it would be a cool idea to create a system which helps the police to prevent disasters like this. The system is quite simple, so I choose it for this presentation. We first created a train set. Basically nothing else with these toy cars. We created a lot of imagery and tagged it manually. So the main enabler for this system was the fact that more and more police departments got their own airborne camera vision systems. And we thought it would be cool if we create a system which tells the operator where are the important places in this situation, because actually we get cool images, but we can't see anything in there. So we wanted to create something like this, which tells the operator, hey, take a look at this place, take a look at these places. These places become quite dangerously dense, and maybe you want to send some forces in there to ease the situation. Our train set was manually tagged, so basically we created several hundreds of images and tagged them by hand, and we trained a neural network with this. So basically, the same with our toy cars, we took a network and we showed them a lot of pictures of crowds. And we forced this network to create a second image where every bright dot represents one person, the position of one person. The resulting system was able to track and find, of course, persons. The whole training process took about 3 days. We took about 6 million iterations. But after this 6 million iterations, where we tried to figure out how our thermostats work, we ended up with a system which was able to find and track persons. And from that moment on, you see every bright dot in this picture is one person. And from that moment on, we were able to calculate very easily the relative distance in our crowd here. And the final system looked like this. You easily can spot the critical crowd situations here, where the most people are. And we are quite happy that in the next 1 or 2 years, this prototype, which was, by the way, developed within 4 months, became a real product, and it will help police to save human lives. And I think this is a very simple, easy understandable, but effective AI approach. And with this imagery, I'd like to thank you for your attention. And if you got any questions left, please feel free to ask.